Hi everyone. Today's lecture on Introduction to Power Electronics. My name is A. Vijay Krishna, working as Assistant Professor in Chebur Engineering College. Today, we're going to discuss about the power electronics and introduction to power electronics. What is a power electronics? Power electronics is nothing but a power conversion by processing electric power to expected voltage, current, and also a frequency with semiconductor devices. That is nothing but the frequency can be changed from 50 Hz to up to what about the required frequency we can deliver the power using the power electronics. That is a high frequency, that is a greater than 20 kilohertz, and these are developed in the 80s. The most applications are the main applications are the industrial, commercial, and residential purposes, electrical vehicles, aerospace, and space technologies. And also some of applications of the power electronics are switched mode power supplies that nowadays we are using in all the systems, computer systems. That is switched SMPS, switched mode power supplies, steady and regulated output voltage or current. The main applications of the SMPS are the low voltage high current DC power supplies, battery chargers, welding machines with over 100 amperes of rating current, and also some of the aeronautical engineering in aerospace applications of power system related towards the power systems and several kilowatt power supplies for radar systems cathode ray. Here, the switched mode power supplies having some of applications of these chargers and also the computer systems. Those are worked based upon the closed loop control for regulating output and also having the advantages of pulse width modulation control techniques and frequency modulation or frequency phase modulation control, microprocessors, DSPs, range of operation concern. If you consider in the diagram, if you observe the diagram, there is input power has been given towards the high frequency converter and from that converter is giving towards the load. Here we consider feedback path. The feedback path is taken for the switching control circuits. This switching control circuit consists of a pulse width modulation technique or a frequency modulation or phase modulation control. This is nothing but a control circuit. Here, the control circuit is also provided with the external control signals towards that is considered as the reference values. Which are the reference values? These reference values are given with the feedback towards the switching control circuit, which consists of a pulse width modulation techniques or phase modulation control techniques. And these gate signals are provided towards the frequency converter, thereby giving signals from the towards the frequency converter. The frequency converter may be operated with respect to the switching control circuit. Whatever the signals getting from the control circuit is from the switching control circuit is given towards the high frequency converter and then the low. Some of applications of the power electronic converters of inverters. These inverters, we know that there's inverters which converts DC to AC. In all domestic applications of household applications and also nowadays we are using regularly of the inverters of having a battery capacity with a small capacity. That is inverters, AC current or mainly voltage output. That is a DC to AC converters are also called as inverters. The input for these inverters is to be DC input. And the applications are AC power supplies, AC drives, and also induction heating and electronic ballast. Domestic application purpose and also some of applications in industrial areas or commercial areas. We are giving AC power supplies. And also, if you go for industrial areas, those are the AC drives. We are using the AC drives nowadays. In place of the DC drives, we are using AC drives. Therefore, the inverters are having regular usage nowadays with improving of the AC drives technologies and waveform shaping and EMI control systems. Shaping the input, that is also very much important. Why? Because we require sine input and also square wave input, square wave output, sine outputs. Depend upon the required waveform, we are getting this shaping, waveform shaping. We are using the waveform shaping. What about the applications of waveform shaping? Switch mode amplifiers, harmonic waveform generation systems. And the applications of the EMI control is the power factor correction rectifiers and also some of active filters. Next, uninterrupted power supplies, motor drives, and next motor drives. What is meant by uninterruptible power supplies? These uninterruptible power supplies, which are mostly used for systems, nothing is nothing but PCs, personal computers, whatever it may be, some of them. That is that which converts a DC to DC, DC to DC. These are also called as choppers. We also know that the choppers, that is also DC-DC converters. With the DC to DC converters of charging and discharging the battery with inverter for AC output. We are using an inverter also for AC output. Next, motor drives, choppers for brush type DC motors and variable speed drives for induction motors, converters for brushless DC motors, converters for switch reactance motors. Here, for the special machines, special purpose machines or the special electrical machines, those are comes under the, we are using some of the drives. These are BLDC motors, brushless DC motors, and also some of induction motors and also some switch reactance motors. These are used DC to DC converters and also DC to DC inverters. These are the applications. Motor drives are some of the applications. Next one, energy storage components of a power components considering, that is inductors, capacitors, and also the transformers. Next, active switching devices, MOSFET, IGBT, thyristors, GTOs, that is gate turn off thyristors, and BJT bipolar junction transistors. These are the active switching devices. Majorly, the power electronics, normally we if you consider that is electronic, from an electronic component, if you consider the silicon, germanium diodes or the transistors, which having the rated voltage is to be, which works on the which works based upon the applying voltage of DC voltage less than 24 volts. If you exceed the voltage, the components may get damaged. If you consider the electronics, here, what is meant by the power electronics? That is comes on the power components. From power components, the power electronics can be considered. The power components, which is having that a diode and also the transistor. If you consider the diode having the voltage of thousands of volts and also the kilovolts also, and also thousands of amperes for the switching purpose, we are using the transistor. If you consider that is works on the thousands of kilovolts and also thousands of amperes ratings. That is nothing but the power electronics. Here, active switching devices of a MOSFETs, IGBTs, insulated gated bipolar transistors, is a power switching device. This switch works based upon the switching signals we are applying, towards the gate, Therefore, the switch can be activated or turned on. Here, these switches works based on a rated voltage of greater than nothing but that is a 1000 volts. Not it should be greater than 24 volts. For example, greater than 24 volts. That is a should be having rating thousands volts and also thousands of amperes. The MOSFET IGBT switches and box and also thyristors is also called a silicon control rectifier, which is a converter. Here, next power switching devices. That is also the passive switching devices of power diodes. That is a general purpose diodes, ultra fast recovery diodes, Schottky barrier diodes. These are some of the diodes. With a why high frequency we are considering, that is with improving of the frequency value, with improving or the increasing of the frequency value, the size and the device or the device can be becomes towards a prototype. That is the main important advantage while we are going for high frequency. That is small size and lightweight. If you consider inductors having the power power loss, power in inductor towards inductor, that is a half Li square, that is the storage, half Li square, Fs square, Fs. And next about capacitors, you consider power storage in the capacitor half Cv square into frequency. That is, if you consider observing the diagram, energy in towards the storage device and also energy output towards the inductor and also the capacitor, which is also storage component equipments. The next one, the characteristics of the active switching devices, showing the symbols of active switching devices. That is the thyristors, BJT MOSFETs, and IGBTs, GT-cores. Showing that first diagram thyristor, that is also called as an SCR, silicon control rectifier, showing that anode, cathode, and also gate. Towards the gate, the signals are applying. The switching signal while we are applying towards the gate. Therefore, the circuit, the switch should be in a turn on condition, comes into turn on condition. The next one also is a BJT. BJT having the diagram symbol, that is a base, collector, and also the emitter. Normally what we observe the electronics, that's the same as the BJT. The next one, the MOSFET, metal oxide semiconductor field effective transistor, source and also drain, and also here also we are giving a gate signal. The next one, GT board, gate turn on, gate turn on. Next one, anode and also the cathode and gate is also provided. Next one, ICB, insulated gate, bipolar transistor, collector, emitter, and also the gate. These are the symbols of some of the switches, power switches. Next one, how the characteristics of the active switching devices are observed. That is, these SCRs are developed in 1960s, and after 1980s it should be becoming very popular. Therefore, switched on by a short injecting gate current pulse, that is a firing or the triggering towards the gate. Switched off when reverse biased. And also ratings up to 5 kilowatt and 4000 ampere. That is the power switching devices ratings. Very high power applications we are using. Therefore, in electrical power systems, we mostly use these are the switching devices for conversion and also the inversion. So if you consider for the HVDC, high voltage direct current transmission systems, we are converting into DC and is also converting into AC again. In a transmission system, we are converting into DC, and after distribution, we are converting it again to AC. Therefore, highest amount of switching uh, highest ratings can be ratings devices can be used here. Therefore, the rating should be 5 kilowatts and also 4000 amperes. This is the ratings, and around 2 volt on state voltage, and a slow response, that is frequency less than 1 kilohertz. Force combination is necessary. These are the some of the characteristics of the active switching devices of the SCR. Next, for the bipolar junction transistor, here showing that uh, two junction, three layer device, the NPN, and also base emitter collector has been provided here. That is a bipolar junction transistor controlled by a base current. Normally, for an SCR controlled by a gate. Here, controlled by a base current, on and off only. And here a linear region is avoided. Ratings up to 1 kilovolt and also 4000 amperes, very high power applications. On-state voltage greater than 1 volt and frequency less than 5 kilohertz. Compared to the SCR, it should work on the less than 5 kilohertz also, up to less than 5 kilohertz. Faster than thyristors. Activating of with nothing but response of the switches should be compared with respect to the thyristors and also the BJTs having faster. Therefore, it is BJT having a faster response compared to the SCRs and slower than MOSFET and IGBT. These are very rarely used. Normally, we mostly in the application point of view, we use the MOSFET and also the IGBTs. Next one, the MOSFET, metal oxide semiconductor field effective transistor or metal oxide silicon field effective transistor. It may be name it as a full name. The next one, it should be developed in early 80s. And normally SCR, these are the devices comes under the Silicon control rectifier family, that is a thyristor family, the SCR family comes under this group. Here, the SCRs can be are designed in 60s, and the development has been going towards the MOSFET of ICPTs in 80s, becomes in 80s. Therefore, developed in early 80s, controlled by gate to source voltage. Gate to source voltage. If you observe that, if you observe the symbols of the MOSFET symbol, if you observe gate to consists of a gate, drain, and also the source. It should be, it is controlled by gate to source voltage. The gate signal and also 10 volts to 18 volts is required. Typically 15 volts it should be for turn on purpose, turn on processor, and ratings up to 1000 volts and 2000 amperes. Next one, high current, low voltage applications, switched mode power supplies, battery charges, and very fast response. FS, the less, it is a less than 1 megahertz for soft switching purposes. Bidirectional resistive conduction characteristics, having the characteristics bidirectional resistive conduction characteristics. Next one, gate turn-off thyristors. These are developed in mid 1980s and similar to same thyristors. If you observe the symbol diagram of that particular gate turn-off thyristors, here gate turn-off thyristors having, if you observe the symbol also same, cathode, anode, and also the gate. If you observe, gate gate signal has been given here, and also the anode and cathode. Here, developed in mid 1980s and similar to thyristor, switched on by injecting short gate current pulse, switched off by reverse bias, switched off by high-end short reversed current pulse. Can be off. Next one, ratings up to 4 kilovolts and also having a current ratings of 3000 amperes and high is high applicable for high power applications. On state voltage to be 2 volt to 3 volts. Response faster than thyristors, and that is the frequency less than 2 kilohertz. Next one, characteristics of the IGBT. IGBT, insulated gate bipolar transistors, developed in the 1980s. Combination of the MOSFET and BJT is nothing but the IGBT, insulated gate bipolar transistor. Whatever the advantages have been considered here, and so some of the drawbacks are considered from the MOSFET and BJPTs are included in the IGBTs. Make the whatever the drawbacks make into advantages and considered and developed the IGBTs controlled by gate to emitter voltage, same as a MOSFET. Normally, MOSFET has been controlled by gate source voltage. Having the within the symbol, if you observe, gate drain source have been placed, and here the gate source voltage controlled by gate source voltage. Here, gate to emitter voltage can has been controlled in the MOSFET IGBT. So ratings up to 3500 volts and also 2000 amperes, medium to high power applications up to 200 kilowatt. Popular in motor drives. These IGBTs, insulated gate bipolar transistors, are popular, very most popular in motor drives. Nothing but AC drives or the DC drives. Most of the applications by using these IGBTs. Next, the on-state voltage have been 1.7 volts and to 3 volts. Fast response, having less than frequency less than 40 kilohertz. Some of the signal diodes, if you consider, that is a Schottky barrier diode, general purpose diodes. If you consider more complicated structure, much higher voltage and current ratings, used in power processing, low frequency response, higher on-state voltage, that is a forward voltage. Nothing but if you consider the power diodes, if you observe use in electrical power systems of a power diodes, without a controlling nothing but if you observe that gate IGBTs, MOSFETs, and also some of the BGTs, if you consider, they have controlled components. There is a gates, base, and also some of the gate signals which we are giving the gate current pulse or the gate pulse. Therefore, that is to be getting turned on and also the turn off procedure. But if you consider the power diodes, there is no controlling part. That is only we are having the anode and also the cathode only. Therefore, therefore, having a response, it is a low frequency response, but it is also having a complicated structure. Next one, if you consider the characteristics of the power diodes, if you observe, the forward bias, low forward voltage drop, and temperature related, and also it should be observed that 0.2 volts to 3 volts. on state voltage it's to be 0.2 volts to 3 volts, decreasing with the temperature increase, and it should typical to provide typical here typical VF has been shown in the data. If you observe, the characteristics has been drawn with respect to the voltage on x-axis and also current in y-axis, y-axis, current in y-axis. If you observe the forward bias and also reverse bias, if you observe having that reverse leakage current here, the small value, and also after having the breakdown voltage point, here the curve should be drops towards the negative side with a zero value, increased value. The voltage has been increased very much in the reverse biased condition. That is also a drawback. Up to the forward voltage, it should be nothing but 0.2 volts to 3 volts up to this point VF value. Here, the curve should be increasing after that. The power diode can be turned on up to 0.2 volts to 3 volts value, on-state voltage value. After it should be increasing up to the rated current value. Next, if you reverse voltage has been applied here, having a breakdown voltage of some value. After that should be increased condition. Reversed bias condition, if you observe with respect to the temperature related, reversed leakage current microampere to milliampere increased with increase of junction temperature, increase with increase of reverse voltage. In if you if you observe, with increasing the junction temperature and also the reverse voltage value, the temperature values are increases here. Here, if you consider with respect to this voltage, reverse voltage, increased reverse voltage, and also the reverse current value on x-axis and also the y-axis, if you observe, with respect to the temperature increasing, what should happen? 25 degrees Celsius having the temperature value, a small linear curve increasing. After 100 degrees Celsius, with reverse current increasing up to this much value, and the increased voltage also at the same time. And also, junction temperature is also increasing up to 175 degrees Celsius. This is also under reverse biased condition. Choosing the reversed applying of reverse voltage is the most dangerous value with respect to the temperature. Next one, junction capacitance. Diode has a capacitor in a reverse biased condition. Diode has a capacitor reverse biased condition. Junction capacitance between the anode and cathode has been observed. That is CZ, C suffix Z, junction capacitor. Here, if you consider the parasitic oscillations are caused solved by the resonant converter techniques and also acting as the resonant component, decreasing with the increase of reverse voltage. Here, these values can be decreasing with the increasing of the reverse voltage. And forward recovery of a power diode, if you consider, during the change from the reverse bias to forward bias and forward voltage VF increasing and back to normal, affecting high current and high voltage systems, not affecting low power system. If you observe with respect to the time period, the forward voltage and also the forward currents, here if you observe that the curve has been slightly increasing after some time, forward bias voltage, forward voltage, the value, the curve has been decreasing and it should be coming towards a steady value. And next, the current is also same way, comes towards the steady condition, up to 10% having a small rise, and after the up to 90% value should be increasing gradually, and after it should becomes to linear, steady condition. Reverse recovery of a power diodes. If you consider the reverse recovery of a power diodes during the change from forward bias to reverse bias, conducting for a period, minority carriers remaining in PN junction and ignoring it less than 400 sine wave, affects significant high frequency and square wave, increasing with increase of IF and DIF by dt, increasing with switching losses and peak reverse voltage of a diode. Types of power diodes, if you consider, that is a general power bus diodes, highest reverse recovery for low frequency applications, ultra fast recovery diodes having a very short reverse recovery period, soft recovery diodes with a lower peak recovery voltage, high frequency and high voltage application. Types of power diodes comes from spotty barrier diodes also. No reverse recovery, highest junction capacitance, lower voltage ratings, more expensive for high frequency, high performance, and low voltage application. And if you consider the junction capacitance of the MOSFET and also the IGBTs, if you consider all devices having junction capacitance between the junctions of anode and cathode. Normally, the MOSFET and the IGBT junction capacitors having the input capacitance, which is equals to CGS plus CZD. That is the gate to source and also the gate to drain. Why? Because these are the two components which we are placing in between the gate, that is the drain and source. Therefore, the capacitance between the gate to source and the gate to drain has been both are added. It comes into additive. There to gate to source and charging, discharging when device is switched on and off. Output capacitance comes under CDS plus CZD. That is the drain source capacitance and also the drain gate capacitance. Switching loss and resonance when off condition. Reverse transfer capacitance, that is CZD, which is equals to the CZD. This is called as a Miller effect. Gate drivers for MOSFET IGBT considered the shorter turn on and turn off, the lower conduction losses having. And totem pole has been placed here. High output current for charging up to input source quickly, and having that controllers we are using ICL 7667, MC34151, MC34152, logic, and also high exit and low exit output, having a high input and also the low output zero greater than 0.4 amperes up to 500 kilohertz having a frequency. Non-floating gate drive circuit, if you consider gate emitter connected to ground and limiting charging current of junction capacitor, damping switch swing of VGS 8 to 33 ohm suggested, and speeding up to discharging of junction capacitor 1 kilo ohm to 10 kilo ohm, suppressing VGS transition voltage rating, peak voltage output of a DR. Next, gate emitter connected to ground, small pulse, 1 is to 1 having a transformer, so having a equal transformation ratio for an that is an isolation transformer. C1 filtering DC component of output of a DRA, and C2 recovering the voltage from DC to AC square wave, that is up to 0 volts. If you consider that the signals which we are here within the diagram, if you observe the signals which we are giving towards the signals towards the input supply input towards a diode, and this is nothing but a light emitting diode. This light emitting diode connected towards a transistor, and it should be activated. And this is a and here isolated DC power supply has been placed here. This is an optocoupler electrical isolation, very low power isolated DC power supply, powering off and DR. Conduction characteristics and conduction losses, if you observe forward voltages, diodes, IGBTs, BGTs, and thyristors. Here observe that the devices which we are showing, the diode, thyristor, and IGBTs, this is the conduction equivalent circuit for these three circuits, switches. That is IA current has been providing, and it is the forward voltage. That is conduction loss is to be equals to product of VF and IA, and some of resistive components of the inductors, capacitors, and also the MOSFETs. Here, MOSFET switch and also the inductor capacitor has been shown. Conduct equivalent circuit shows here having that drain source resistance, having that, and also the conduction loss is to be Ia square RDS. And here having the same for the inductor and capacitor having the same Ia square R losses, and which is equals to the current value. Ia current value is to be RMS value, that is root mean square value. Most power losses of devices converted to heat is to be heat dissipation for long lifetime of devices, too small surface area to float heat to surrounding medium. And cooling devices, some of the air convection cooling, low to medium power heat sink, pinned aluminum increasing. If you observe here, this is the heat sink, which is also having a heat sink here provided here. Normal all the inverters which we are placing here, these are the cooling devices for the device of IGBT switches or the MOSFETs. Here the fins are placed here, the natural air moving towards the fins, and after the air is to be convected air is to be coming outward, that is convection. In the cooling has been considered as a convection process, that is a convection cooling, and this is completely heat sink. Low to medium power, finned aluminum, increasing surface area, decreasing thermal resistance. And with using of the airflow towards the normal natural air has been using. If you use any fan, a small fan for a cooling purpose, therefore uh, the device cooling percentage cooling has been increased. Therefore, the temperature of the device can be reduced. Here, the temperature change of temperature of the device can be shown here. The change in temperature value T suffix j minus Ta is equal to P loss of Rjc plus Rch plus Rhe. These are the resistive values. And this is nothing but the introduction to the power electronic devices of some of the switching devices and also the power diodes has been discussed. Thank you.